and I didn't push any buttons, I did not energize this thing here, my dishes would not come clean, would they? Because there's no source that would energize the function of this thing that we call a dishwasher that's properly termed as an appliance. We need an energized source to function as what the appliance is supposed to do. Down here, if I said, okay, I got this jetted whirlpool thing here, do I have to engage the motor in order to sit in this thing and take a bath? Do I have to do that? Do I have to engage this particular thing in order to just kind of like get into it and soak in it? The answer is no.
No.
The answer is absolutely not. It's properly termed as a plumbing fixture instead of a plumbing appliance. Okay, so dishwasher is a plumbing appliance because the jetted whirlpool tub does not depend on, here we go, energized components to be a bathtub. So the tubs in this case are considered plumbing fixtures. However, there are requirements for the electrical motors, things of that nature, to function as such. But in terms of the plumbing code, it is considered a plumbing fixture. Okay? All right. Plumbing fixture, by definition, a plumbing fixture could have only a water supply connected to it, only a waste line connected to it, or both. Okay? Good things to understand. You know what a plumbing system is? A plumbing system, look at this. It includes everything. The distribution pipes, the plumbing fixtures, the traps, any kind of water treating, soil waste, vent pipes, drains, etc. It's the whole system. They can be classified in different types of systems as well, like the water distribution, the water supply, the drain, waste, or vent. Here's a good definition you need to know. You need to know this right here. It's called a waste receptor. You know what a waste receptor is? Look at this here. This is the back of the box. You know what this box is, don't you? This is a washer box, right? I've got this thing here, this vertical pipe. We call it a standpipe, ladies and gentlemen. This is where you take that rubber hose from the washing machine or plastic hose and stick it right into that vertical pipe called a standpipe. Does that fit the definition of waste receptor? It sure does. That was a new change. We added floor drains and standpipes to everything else, right? Like trench drains, hub drains, service sinks. This is a definition that we use for taking maybe condensate, maybe washing machine waste into these devices here that are piped in that are called waste receptors, floor drains, standpipes, things of that nature. All right. Any questions before we move on? We're done with definitions for now. Let's move on. Let's talk about the water service piping inspection. We have two tasks here, ladies and gentlemen, material inspection and installation inspection. Now, I want to show you this. This is what we call a private supply system, in which case that we have a well, a boring that's actually drilled into the earth, ladies and gentlemen. We actually drill down into the earth till we hit what's called an aquifer, right? That's probably a layer of water trapped in different strata, like rock strata, soil strata, things of that nature. And we stick a submersible pump all the way down the pipe shaft here. And that submersible pump, when it's called to produce water, maybe by a pressure switch here in the house, it energizes that submersible pump and draws water up through a pipe or a tube that comes in through a pressure tank in order to supply the potable water to the dwelling. That's a private water system. The next one that you see here is what we call the water service pipe. This is where we connect up to a city public main water supply system. In a case like this, the water supply piping is probably right where it ties into the city main, and it goes all the way to this valve. Remember that demarcation I was telling you about earlier? Here it is. This is considered water service or water supply piping until it gets to the water service valve. When it comes out of the water service valve, it's called water distribution piping. Know the demarcation here, okay? That's exactly what we're looking at. Now, I don't know about you, but I don't want to have a water meter. Do I really need a water meter? Sometimes you do, right? On municipal supply, right? What's a water meter used for? Water meter?
Bill you for water served.
Well, I don't want to be billed for water, Jamie. Do I really need a water meter?
You don't get a choice sometimes there, Jerry.
I don't get a choice. You're absolutely right. The utilities, oh my gosh, they have to bill me just like the gas meter and the electric meter. Unless you got a private well, right? Then you don't need one. But anyway, this is showing maybe a couple locations. We see them up north here, normally inside. We may see them down below the frost line in chambers or boxes at the water main itself there, maybe just off to the side in the right of way. But you can see them basically in chambers at the street or inside the dwelling units. Now, please highlight your code book. Please understand this. This is your pressure limitation. You are never, ever allowed to exceed 80 PSI on a water distribution system, period, because your fixtures are not rated for this. Here it is. It's in chapter 29, 2903.331 to be exact. The static water pressure cannot be greater than 80 PSI. Well, what do you do if I have a situation like this? Here you go. I got 100 PSI coming from my main into the house here. I've got to find a way to reduce it. What we need is what's called a pressure reducing valve here, and this is what it is here. Looking at it this way here, it's basically a valve conforming to a standard, the American Society of Sanitary Engineers. It's called ASSE 1003 or the CSA alternative standard as well. This is our guarantee. Because you know what? We live in the United States. We have standards to follow and codes to follow. That enables us to design and build a safe plumbing system. Here's my supply pressure coming in, 100 PSI. I could take this screw, either depress or uncompress the spring tension here, and it will regulate the pressure coming out of this particular valve. So I can go from 100 and I can set this thing to 60 PSI, 50 PSI, cannot be greater than 80 PSI. Some of the materials that we see out here, I have an example here for you. I wanted to show you this here. This is a plastic material here. It's called polyethylene. You may see this, you may not. Just wanted to show you how the plastic piping industry shows labels and what these actual indications mean on the piping. If you're a plumbing inspector, you need to know this. I'm going to show you tables in the plumbing code that we look at as well. So for this, we're looking at, hey, they should designate the pipe size, the nominal pipe diameter. If I'm an inspector, I'm looking at the approved construction documents when I go out and do any inspection. In other words, something's got to be approved at the building department. If you're taking your code book out on the job site and looking at your code book to try to determine compliance, I'm telling you, you're going at it the wrong way. Submittals need to come into the building department. They need to show you what they're actually doing on the proposed building. Like an isometric drawing, maybe a water supply drawing, water distribution. Show me the pipe sizes, show me the materials. That way, when you go out to the field, you're looking at the correct pipe size. The manufacturer will have its indication on here. They'll show you the pressure of the piping or tubing, the rated pressure. They'll actually show you the copper or iron tube size, and they'll actually indicate this thing right here. Is this material suitable for potable water? It needs to be for water distribution and water supply piping. National Sanitation Foundation -PW. This is what you always want to look for in these materials. Along with that comes an ASTM specification. That's a test standard based upon this material. In this case, for example, this is polyethylene material right here. ASTM material classification is 2305. Now this SDR right here, this is a ratio, ladies and gentlemen, that helps determine, the pipe pressure. What do I mean by this? The SDR, standard dimension ratio, you find this only in plastic piping, not in metal piping. It's a determination based upon the outside diameter, right? The outside diameter from here to here, right? Divided by the wall thickness. Divided by the wall thickness. Now, right here, here's what it means here. If I've got a high standard dimension ratio, the pipe wall is thin compared to the diameter, right? With a low SDR ratio, the pipe wall is thick compared to the pipe diameter. So realize, the thicker the pipe wall, the more pressure that we can carry in the pipe, correct? The thicker the wall, the more pressure, right? So standard dimension ratio is given to you in a decimal like this, all right? Making sure that they use the right pipe and materials. All right, what we're going to do here is we're going to take a look at task number 1. Let me bring our workbook here as we navigate through here, make this bigger, and I'll navigate down. Here's where we're at right here in the flow chart. And what you see here, there's a whole bunch of code sections here in your workbook that we're going to actually reference. It's good for you to maybe make some notes here on different types of piping for our system, okay? You also have an area here with some good common terms for our discussion here and a few steps. We have 5 steps here. Number 1, we're going to verify that the water service line is an approved material, right? We're going to verify that the water service line material is suitable for ground conditions as well, and the location of any water valves that need to be placed on the water service line. And last but not least, joints and leak checking, etc. You have in your workbook this particular table here, and it's referenced in your code book as well. Let me make this a little bit bigger so we can see it here. This particular table here, water service pipe. You have a code section here and a page number. I want you to look at the left-hand column here. These are the approved materials for water service pipe, outside, maybe underground, connected to the city main. On the right side, the standard. This will be indicated or stamped on the pipe. When you go out there to do the inspection, you look in the trench and say, okay, that matches up with the approved construction documents, the pipe size, but does the standard match up with the material? Okay. You have a section here called copper or copper alloy tubing. You know what that is. Has everybody seen copper tubing before? I'm going to highlight that. We have, haven't we? Jamie, I got a question for you. This one's for you, Jamie. Are you ready? All right. Yeah. All right. So we're all familiar with copper tubing. Jamie, I want you to look at this here. We have a selection to make. So if I'm the designer or the plans examiner and somebody comes in here, they can specify any of these types of copper tubing. Type K, WK, L, WLM, or WM. What am I looking at here, Jamie? What do these mean? Do you have any idea?
Well, let's see, going off memory.
Yeah.
Has something to do with the thickness of the pipe, right?
Yes, it does. Absolutely. It's the wall thickness of the pipe, right? So K, type K, if you're taking notes, ladies and gentlemen, type K is the thickest wall copper tubing. Type L is your next one down, and then type M is your thinnest that's allowed to be used. Now, there's color codes to this. Copper tubing is a copper color, right? The manufacturer stamps their stamping with colors, okay? A type K is, okay, I'll let you guess. What color do you think type K is stamped by the manufacturer? Color code. Not blue.
Red.
Green. Type K is green. So if you're taking notes, the code doesn't tell you this. This is manufacturing standards here. Type K is green. Type L is what? Take a guess. Color? All right, it's blue. Yeah, type L is blue. And then type M is... Type M is red. Type M is red. So I got green, blue, and red. All right, who do I kind of ask next here? I don't know, Edwin. What do you think, Edwin? I see K copper, but then I see WK. What the heck does W mean? Any idea? Carla, Don, Harold, Jamie, Boudreaux. What does the W mean in front of WK, WL, or WM? You're going to hear it from a contractor. Well, you're the plumbing inspector. You should know what this means, right? You should know what this means.
Does that have to do with ground contact?
No. W.
Is it waste?
Waste? No, that's a good guess, though. No.
It's weight.
Yeah, it would make sense that it would be for water, right? But it's not.
So weight.
There's two ways to manufacture pipe, okay? One is what we call an extruded means, right? Where we take like a, I don't know, like a rod and we run it through like a mandrel, and all of a sudden it just extrudes, it pokes a hole right through a solid piece of material. The other way is what we call welded seam pipe, where we use plate, ladies and gentlemen, and we wrap it around a mandrel and then we weld it longitudinally. It's called welded seam pipe. You see what the W stands for now? Welded seam K copper, welded seam L copper, and welded seam M copper. You could actually see the longitudinal seam in it. So each one of those can be used, all right? That'd be a great Jeopardy question, wouldn't it? Look at all the other materials that you can use for water service pipe. You see this right here? I mean, I'm looking at this and I'm saying, man, this is great stuff. But I don't see a material here. Can I use cast iron pipe here? Can I use cast iron? Can I use cast iron for water service pipe? Absolutely not. Absolutely not. You know, this isn't for potable water, ladies and gentlemen. These are the materials that can be utilized. Now, understanding that that table exists, let me continue on and get some more pictures up here so we can make sense of this here. What we're going to do is we're going to make sure that we have all the valves. I'm going to make sure that the joints are made up correctly. When we look at pipe joints, ladies and gentlemen, kind of like this, I don't want to skip around here. Let me get back to the workbook. But in order to join piping materials together, we need pipe fittings, right? Certain types of pipe fittings, okay? So we have a table that's associated with the pipe fittings, and if you kind of look at it, look what's happening here. We have the same materials that we're going to be using as far as the piping. We have the pipe fitting chart as well, and we have the standards that go along with the pipe fittings for materials. It kind of makes sense. So we talked about copper, right? You know, I still see a little bit of copper. What type of piping do you see underground coming from your city main to buildings? What type of materials do you see?
Polyethylene.
Hang on a minute. Somebody's breaking up. Let me check the audio here. Okay, go ahead. Yes. So we're seeing all different types of materials out there, right? In a case like that, you know, certain maybe water departments regulate the water, or maybe you do in your building departments, things of that nature, you know. We're concerned with, you know, how this stuff is fitted up as well, you know. Here's a soldered joint here that may be usable if we have copper tubing underground, like K copper or something. Maybe it's not long enough to get to the house. We roll it out. Maybe it's soft copper. We got to put a coupling in here. How do we do it, right? Well, we clean the ends up, right? Real good, sand them off real good after you deburr the piping real good after you're done cutting it, right? And then you put some flux on it, right? And you solder the joint with lead-free solder, right? One way to do it. Plastic piping, these are called solvent cemented joints here. PVC, CPVC, you see this all the time, right? You cut it, you clean it, you glue it. Everybody's a genius. Isn't it easy to do this stuff, right? Right? Pretty simple, right? Using the correct materials and making sure it's leak-free. We have this thing here called a dielectric union or a dielectric fitting. We do not want dissimilar metals to be in contact with one another, like iron-based materials to like copper or those type of materials, because we have what's called galvanic action, corrosion that could occur with dissimilar metals. You need to isolate these materials. Case in point, where we normally see these at are on the water distribution side, like around water heaters, right? You come out of the top of the water heater with some carbon-based pipe, or a nipple, if you will, and then you transition to copper tubing. You don't want the iron-based material to come in contact with the copper tubing, because we have the proverbial anode-cathode thing here, which the corrosion is always going to be the iron-based material. That's the sacrificial lamb here, okay? It will corrode and leak. So we need this thing that we have, maybe like a rubber type of a gasket here, and we have plastic inserts here that we actually isolate the copper material from the iron-based steel material. This is called a dielectric union. Now we have dielectric nipples with a plastic insert all the way through these dielectric nipples that do the same thing. All right, let me move on to just one more thing here for our discussion. And I'm going to open up my code book here. All right. Verify that the water service line, the joints and connections do not leak under pressure. Ladies and gentlemen, if you have a code book, go to chapter 25. Go to chapter 25, specifically 2503.7, because this is where you're going to get the testing for the water supply system right here. Take a look at this here. And it tells us right here, upon completion of the water supply system or a section, the system or portion needs to be tested. In other words, to prove it watertight, not less than the working pressure of the system for piping systems other than plastic, by an air test of not less than 50 psi. How long does it need to be held for? 15 minutes, right here. So any water used for tests shall be obtained from the potable water source. There you have it right there. If the piping or tubing is other than plastic, I need, and if I tested it by air, not less than 50 psi. You have to be careful with plastic piping, ladies and gentlemen, don't you? What happens if I used, I don't know, like PVC, and I applied an air test to PVC? Maybe I'm a plumbing contractor. I've been doing it for 50 years, and I'll say, I'll show that new plumbing inspector that I don't have any leaks. I'll pump that thing up to 500 psi. What do you think will happen to PVC pipe under that type of pressure, ladies and gentlemen?
Failure.
It will explode, right? And the shards and the shrapnel will injure people and, you know, cause a lot of damage, you know, bad stuff. It's been coming out not only in the plumbing code, but the mechanical code for the past several years now. You have an exception here for PEX piping systems. All right, let me clarify. You've heard PEX, we know PEX, you've heard it, but what is PEX, right? Cross-linked polyethylene tubing, cross-linked. It's the chemical kind of a thing that they do, and it's plastic piping. We see this for water distribution and water supply piping all the time. So understand, chapter 25 is our section. Here we go right here. You have the pressure rating of the water service pipe right here. And it indicates in chapter 29, 2906.4, the water service pipe needs to conform to NSF 61. National Sanitation Foundation. It's a certification indicating that the water service pipe is acceptable for use for potable water. Fantastic. That's the standard and the certification. And it's got to conform to one of the materials indicated in this table. We saw that table, didn't we? That's where we saw the copper tubing and all those other materials that we can use, right? Except this would be a great test question, wouldn't it? If you're taking an ICC exam, boy, I'll tell you what, if I was developing a test, I would ask this question. It shall have a working pressure of not less than, here it is, 160 PSI at 73 degrees Fahrenheit, right? So if the water pressure exceeds that amount, right, the piping material needs to have the rated working pressure according to that particular pressure. So keep in mind, these are quite valuable when you're doing your plan reviews, when you're doing your inspections, if you're an architect or engineer, when you're specifying materials accordingly. I want to show you this. Let me show you this because we're talking about the water supply. But before we, yes, question. Oh, sure, go ahead. Yeah. Oh, absolutely, without a doubt. Right, right. Keep in mind, we're not talking about this. This pipe is not in the house yet, Chris. This pipe is out underground. It's being connected to a city main. This is called the water supply pipe. We're not in the house yet. If we are, we're up to the water service valve. It's after that point that we need to reduce the water pressure on the water distribution side. Does that help, Chris? Good question. Yeah, yeah. So this is the water service pipe. So, I mean, we're at the mercy of the city main here because we can't put a pressure reducing valve at the street. We do that normally inside the house before we start our water distribution piping. Good question. All right. Any other questions before we move on? Okay, good. So we're just kind of piecing the system together right from the beginning here, making sure that we understand it, making sure that we understand where the code sections are. Here's all our materials that we discussed along the way. Now, right here, you have some common terms I want to bring out to you right here. And we have this thing here called firm bed here, okay? Pretty simple. It says rocky or unstable soil shall be over excavated by 2 or more pipe diameters and brought to the proper grade with suitable compacted granular material. I say, okay, well, what are we looking at here? If I look at this particular trench here, it looks like somebody took a backhoe and cut a trench into the earth for a proposed pipe to be bedded on that we call the water service pipe. Okay, so when we look at this, I come over here and I say, okay, let me get my code book out here. Let me find my code book real quick here. Maybe this is a good question for you while I'm looking for my code book. What section in the IRC do you think you need to go to for this trenching and backfilling and all that other stuff? What do you think? Well, like you, I can't remember every section of every code, so I go to the table of contents or I'll go to the index and look for a word. But in this case here, I'm going to go right into the table of contents right here. I'm going to say, okay, trenching and backfilling. Excuse me. Right here. So I'm in this particular chapter, section 2604, right here. You see this right here? When we look at that trench that you see in your workbook, we're looking at, hey, we want to have a good trench to bed our pipe on right here. And it says specifically, just like that definition gave us, right, for firm, suitable thing here, rocky or unstable soil shall be over excavated by 2 or more pipe diameters. Excuse me. Now, How do we backfill the pipe? This is important right here. We backfill by having good, suitable material. That's all the code tells you. Well, what's good, suitable material? The code doesn't specify anything. What do you think is good, suitable material? Beer cans and construction debris? What do you think? Is that suitable material? Absolutely not. Maybe some fine sand, fine gravel material, things of that nature. I want to bed the pipe on. I want to set my pipe on that and backfill it. Suitable material. But here's the catch. Look at here. Not a lot of people realize this. It says right here, backfill shall be free from rocks, broken concrete, frozen chunks until when? Until the pipe is covered by what? Not less than 12 inches of tamped earth. But when you're tamping the earth, we need to take the loose, good earth in 6-inch intervals. So in other words, you put your pipe on the bottom of the trench. Maybe there's some good bedding down there, some gravel, some sand. Then you put 6 inches of nice loose earth, compact it, and then put another 6 inches of earth. That gives me 12 inches of tamped earth, right? That's what the code says. And then afterwards, then what can you put on that? Broken concrete, frozen things, beer cans, construction debris. The code doesn't care at that point because you've locked the piping in accordingly. That's all the code is stating, right? Now, if you're an engineer or an architect or a designer, you're going to say, that's crazy. I want nice clean fill all the way up to the top, don't you? Right? But the code is giving you the limitation. So please understand, you need to go to this section for all trenching and backfilling. Okay, now that we understand that, we kind of run by in the tasks here. Let me get rid of that stuff here. And we move on. Here is, in fact, the graphic that I'm going to discuss with you. Okay, this particular graphic is pretty important. Now, I'm going to get rid of the workbook here, kind of keep my code book handy and go over this with you. All right, let me bring the graphic up on the screen here. Here it is right here. You need to highlight this code section here because it gives us everything we need to know about separation of the water service from the building sewer. Okay, we don't want cross-contamination. We don't want to contaminate the potable water supply. So this section, 2906.41, ladies and gentlemen, I'm not going to read this to you because it's like reading a bedtime story. I'm just going to explain it to you. How's that? I want you to look at the graphics here. In general, you need a 5-foot separation between your water service pipe and your building sewer, period. And then the code says, well, you know what? Maybe we could get away with having the water service pipe in the same trench as what? The building sewer. And then maybe it says, well, maybe we can have the water service put on a little 12-inch shelf above the building sewer. Taking a look at this, we'll split it apart. Take a look at this right here. Number one, right here, it says where the building sewer, I'm reading right here after the blue highlight right here, where the building sewer piping is not constructed of materials in this table right here, right? The water service pipe and building sewer shall be horizontally separated not less than 5 feet, right, of undisturbed or compacted earth. So that kind of intrigues me here. If I go up to where it's highlighted in blue, it says where the water service pipe is located in the same trench, kind of like this one here with the building sewer. The building sewer shall be constructed of materials listed in this table. Now I'm going to get my code book out like you, and I'm going to go to that table, and I want to see what that table is. What makes it so special that I pick the material of my sewer from that table in order to allow me to put it in the same trench as the water pipe? Let me get that particular table. So it's 3002.1 parenthesis 2. So I'm going to get my code book out here. I'm going to go to chapter 30. So going to chapter 30, I say to myself, okay, chapter 30 is sanitary drainage over here on the left-hand side. I'm going to go to materials section 3002. Okay, and the particular table that we're looking at is referenced as this one right here. I'll highlight it. Here's the table that's being referenced, isn't it? Right here. This particular table. Is that correct? Is that correct? If I look at that, 3002.1 parenthesis 2, right? That's for the building sewer. That's outside the building, right? Well, it's referencing this table. This doesn't say building sewer, does it? No. Why is chapter 29 right here referencing the water service, referencing a table here for a building sewer that the table doesn't even indicate that that's the building sewer? I'll tell you why, ladies and gentlemen. The table right below it right here is for sewer pipe. Think about this. The material that you do not see in the top table here is vitrified clay pipe. See this right here? See this vitrified clay pipe down here? Do you see that? You know what vitrified clay pipe is? It's clay pipe. It's very brittle. It'll break. Roots get in it. It will displace the joints. It will leak, ladies and gentlemen. Do you see vitrified clay pipe in this table here up on the top? I don't. Do you? This table is a function of maybe better quality materials that can be buried in a trench with the water pipe. That's why chapter 29, that particular section, is referencing this table here, because all of these materials here are far more durable than like a vitrified clay pipe underground, right? We don't want to contaminate the water pipe. That's why this table is referenced in this particular code section right here, and we will be able to provide any material of the sewer based upon that table in the same trench as the water service pipe. You know, if I'm a builder, if I'm an architect, if I'm an engineer, I'm going to do this all the time because I only have to dig one trench. That's going to save me time and money. And if I submit this to the building official for plan review, it's going to pass every single time. Any questions on this? Questions, comments? You plumbing inspectors out there or future plumbing inspectors, you got to know this. This is where you go. Or I could actually use this method right here. Here's the building sewer. I could take the water service pipe, put it on a shelf 12 inches above, and that's right here. See the very last sentence here? So if you're like me, I'm highlighting this code section because I want to know this is nuts and bolts, right? The required separation distance shall not apply where the bottom of the water service pipe that is located within 5 feet of the sewer is not less than 12 inches, there we go, above the highest point of the top of the building sewer. That's this graphic right here, okay? So there we have it. Moving on, again, I'll just show you that table briefly here. That's the table that was referenced for having the sewer pipe in the same trench as the water pipe. All right, now, as we continue our discussion about the water supply pipe, this probably comes from a city main, right? Things of that nature. There's a graphic, I think, in your, there is, step 4, I think, right here. Just above step 4. You see this graphic in your workbook right here? Right here? We need to be careful that we don't have cross-contamination, right? We want to keep the potable water source clean and safe for people to utilize in the dwelling. Now, this is kind of unlikely here that you're going to see this tap off the city main feeding your lawn irrigation system. But let's look at the principle. This could happen whether you're tapping off of the water supply pipe or the water distribution pipe over here. We still need to protect the potable water supply. Now, I'm going to show you something here. Right here. The workbook doesn't tell you all this stuff. I'm here to tell you, go to this section right here, 2902.5.3. It's telling you right here, if you got a lawn sprinkler system, which most houses have these days, you know, higher end houses, you need to protect the potable water supply. Here's how you do it right here. It tells you, it says, you know what? If you go with a lawn irrigation system, you can protect the potable water supply by an atmospheric vacuum breaker, a pressure vacuum breaker assembly, a reduced pressure principal backflow prevention assembly. That's the Cadillac of them all. I'm going to show you an example here in a minute. And it says, however, be very careful. If there are chemicals injected into the irrigation system, like liquid fertilizer, right? You are only limited to the reduced pressure principal backflow prevention assembly, period. You can't use the vacuum breaker or the pressure vacuum breaker assembly, okay? So understand if you have chemical or not. Now, here's how this works. I'm going to show you what's called a pressure vacuum breaker, all right? Let me go back and show you our application. Open your workbook, ladies and gentlemen. Here's your workbook right here. If you open your workbook, you're going to go to this graphic right here. You with me? Does everybody have this open? This graphic right here, okay? I'm going to come in with my water supply into the bottom of this backflow preventer. So in other words, I'm going to pipe in from the bottom, okay? So when I pipe in from the bottom, I'm coming right into this particular port right here to the inlet of the pressure vacuum breaker. Ladies and gentlemen, this is a spring, and the spring pressure holds this rubberized seat down accordingly, right? It's going to be seated. Now, upon pressure coming in, the force of the pressure is going to do what to the spring? What's going to happen when I open this valve here? What's going to happen?
Compress.
It's going to compress it.
Yes, the spring will compress, and guess what? The water will be emitted into this chamber here. But look at this thing hanging here. It's just dangling down here. It's got an open seat with like ports, right? That are open to the atmosphere. It's like a little dome on it. Well, when the pressure increases and it fills this reservoir, what's going to happen to this spring and seat up here?
Close.
Yes.
It'll compress and seal.
It will compress the spring by force of the pressure and seal this top. So the water in this reservoir can only go and be directed to the right-hand side, which is going to feed my lawn irrigation system. Do you see how this works? Right? So I have pressure that's actually flowing to the right, and now it will function to take the water and feed water pressure and volume to these sprinkler heads that you see right here, and it will work normal. Now, let's say, for instance, all of a sudden, we lose water pressure, ladies and gentlemen. The valves are open and maybe somebody's doing a little bit of work on the city water main, and all of a sudden I lose pressure. What's going to happen, right? This spring's going to slam shut, right? On zero pressure. Any kind of muddy, crappy water that's going to be flowing back, maybe under negative pressure perhaps, or maybe just flowing back, will go into this reservoir, and then the overflow will actually kind of seep around here and spill over, if you will, right? It's not going to go beyond this spring because the spring pressure is actually providing a seat here. So the water cannot go back down and contaminate the potable water supply, can it? Absolutely not. It can only spill over this particular dome on this particular vacuum breaker. In other words, it breaks the vacuum, right? Vacuum breaker, right? It's breaking the vacuum and allowing any kind of overflow to seep over the top of that valve. Does that make sense? One way to protect the potable water system. Okay. All right. Moving on. Moving on. We have a frost line here. If we look at this particular graphic here, the burial depth right here for any kind of water pipe has to be at least 12 inches or below the frost level. Let me ask you a question. What is the burial depth in your jurisdiction for water piping? Do you have a frost depth or anything where you're at? 40, Chris, 42 inches. Yeah, that's where we're at in Ohio too. Anybody else?
We have a 42 depth with a preferred 6-foot depth of water line.
Yeah, yeah. So you're going to be subjected to different depths all across the United States. If you don't have frost, then it's 12 inches minimum, according to the code. According to the code. And when we get back into the workbook, we will actually go through this systematically right here. We're going to check the burial depth right here. These are good inspection checklists right here. Now, a lot of times, especially in different states or counties or cities, sometimes if you're the building department, you don't regulate the water supply. Maybe that's the city engineer, the county engineer's department for that type of jurisdiction. They have rules and standards that need to be followed, but in all cases, you need to consult the city engineer's office as well for all of those particular items. Okay, checking the routing of the line. What I want to bring up next is what you see here. You see here. Now, I'm sure you know what load path is. If you're in this industry, you know what load path is. I have a graphic here to show you. It's of the same graphic that you see in your workbook right here. This is what we call the bearing plane, ladies and gentlemen. What we have is, call it a stem wall, call it a basement wall in this application or this graphic here. We carry all the vertical axial loads down to this point on the foundation. They all resolve themselves to this point. When I go below here, now I'm carrying lateral soil load and vertical load, and it's trying to resolve itself all the way down into the footing, right? Where we make the footing large enough in area to accommodate the total load that comes down and transfer that load to the soil below. Well, then we take and draw a 45-degree angle at each side, right, of that particular footer, right? If I take a horizontal plane at this point and go horizontally, I'll measure down 45 degrees, right? We want to keep our piping above that 45-degree angle here that actually is demarcated at the corner of the footing. This is called the bearing plane. This is where we resolve most of, or all of the loads, I should say, from the building. If we put our piping underneath here, now the piping is subjected to pressures that may or may not be adequate for the material, right? So the code says, hey, take a look at this here. Do not extend down into the bearing plane. I'm in chapter 26, right? That's where I found my trenching and backfilling. Remember that general requirement chapter? This is where you find this stuff at, okay? Here's my bedding right here. We looked at this before. I'm going to reinforce it with you here. 2604.1. Hey, piping shall not be supported on rocks or blocks at any point. What are we talking about? We're talking about bedding the pipe. Take a look at this here. We want a nice firm bed along the total longitudinal length of the pipe. We want to support it along its length in the trench. In other words, we don't want to put a rock here or a brick to support the pipe every 10 feet. What would that do for us if we supported the pipe every 10 foot on a couple of boulders or rocks? What would that do after we
Sags in
backfilled
the
it?
pipe?
What was that, Daniel?
Sags in the pipe?
Yeah, it would put bellies in the pipe, right? It would deflect the pipe and it may damage the joints and things of that nature. It'd be like a roller coaster, right? The pipe would be up and down, right? Look at my graphic. See? We wouldn't want that. If it's got to be gravity and pitch down, we want a nice slope as well to get from one point to the other, right? Prevent damage, things of that nature. Water supply. Hey, if you've got copper tubing, here's your standard right here. It's an ASTM standard B88. Been around for many, many decades. You know what? You bend copper pipe, you bend copper tubing with pipe benders. You know, I've seen people do it with their knees and stuff like that. It kinks the pipe. You got to use this. Now, here's how this works, right? It's the radius based upon the pipe diameter, right? So the standard comes in and says, hey, must be at least 4 times the diameter of the tube. So if it's 1-inch tubing, I need a minimum radius of 4 inches here. And we do this with pipe benders to bend pipe accordingly. All right, so let's see here. Oh, let's see what I want to do here. Let me go to this section right here. If I've got a pipe that's going to penetrate through a foundation wall, this code section in general regulations or requirements gives us the minimum pipe sleeve right here. It says it needs to be 2 pipe sizes greater than the pipe passing through the wall. I say, okay, well, let's say that I've got, I don't know, maybe it's a 1-inch water pipe. 1-inch water pipe that has to penetrate through the foundation wall. What size sleeve do I need by code? Another great test question, isn't it?
2 inches.
I've got a 1-inch water pipe.
3 inches? 3 inch hole.
Jamie, you said 3 inches? Anybody else?
No, I'm sorry. If you had a 1-inch pipe, it wouldn't be a 3-inch hole because it's 2 pipe size larges. So
So what is it?
2-inch pipe hole, right?
1.5.
1.5, absolutely right. 1.5, right? Because if this is 1-inch pipe, the next pipe size over 1 inch is 1.25 inches, and then 1.5 inches, right? 1.25 inches, then 1.5 inches. So minimum 1.5 inches, okay? And given the code section, that's exactly what we're talking about. There we go. Step 11, verify the backfill materials are safe to use as backfill for pipe. The code doesn't specify it, right? That's up to the designer to specify. Here's what we were talking about, right? There's our solid bedding right here to support the pipe along its bottom edge throughout the whole trench. And hey, there's our 2 layers of 6-inch tamp, right? Tamp clean fill, right? Again, no beer cans, no construction debris, no frozen chunks, no concrete, right? Above here, I don't know, you can go with all that frozen stuff. The code doesn't care at that point because what we're doing is we're locking the pipe in to this area here with clean fill bedding and good tamped earth, period. That's what we're doing, all right? All right, here's your question right here. Can a water service pipe be located within the same trench as the building sewer pipe? Yes or no?
Yes.
On the shelf, yeah.
Yes.
Yeah.
Yes.
Yes, but when? When can this happen? Absolutely right, Chris.
Chapter 30.
Fantastic. You got it. 10-4. And this is the table. You remember this, right? Again, this table is going to come up all the time. Whether you're an inspector, a plans examiner, you got to check this stuff. Or the city engineer, you better take a look at this. You know, unless you have your own standards or you use the International Residential Code standards, things of that nature. All right, next question. What is the minimum working pressure permitted for water service pipe?
160D.
D, I hear. Anybody else? Weigh in.
Isn't 80?
All right. Yeah, that's right, Chris. But I'm asking one simple question here, right? What is the minimum working pressure permitted for water service pipe?
Is there a minimum?
20 PSI, isn't it?
160 PSI at 73 degrees Fahrenheit. That's what it is, right? Water service pipe, not water distribution pipe, water service pipe. There it is right there, 2906.4. And lo and behold, look at this. We got a nice checklist here. Now, I'm a big fan of checklists, especially when I
Sorry,
do.
could you go back one slide? I tried to get that code.
Oh, yeah, I'm sorry. Yep. Let me go back. All right. All right. So we recall this section 2906.4, which we stated before. Remember, this is from like a city main going into a residential dwelling. Our pressure needs to be at least 160 because we don't know what our city main is. If it's over 160 PSI, remember, it says right here that if it exceeds 160, then the material that you're using must have a rated working pressure equal to or greater than the highest available pressure. But in general, it needs to be 160 PSI. Okay? All right.
Yes. Thank
Moving
you.
on. You have checklists available to you in the book here. And I like this because I use checklists in plan review every single day. It helps me keep on track so I don't miss anything. And I like this because we have the tables and the code sections integrated into the checklist to help you out. Now, if you're studying for an exam too, I would kind of use this as a good tool for you to help study for the exam regarding this particular system that we call the water service pipe for inspections, code sections, things of that nature. All right. So here's my plan. My plan is to take lunch in about, I don't know, maybe about 35 minutes or so. But what I want to do right now is I want to take a quick 10-minute break and then come back in and introduce this before we go to lunch.